welcome everyone, and I have the pleasure of introducing Clara this week. She did her undergraduate studies in Twente and then did a PhD through the Networks program, which is also where I did my PhD. But she was in Eindhoven while I was in Leiden with Remco van der Hofstad. And she ended up writing a thesis that is, I think, 357 pages long. So that's quite a tome. And that resulted in 14 publications. So very productive. And that meant, of course, that she immediately got a position as an assistant professor at the University of Twente. And recently, she was awarded a Veni grant, I think last at the end of last year. And we're very happy to have her. And please go ahead, Clara.
So yes, thank you for this introduction. So let me see. Yes, I can still see you. Yes, okay. So I'm very happy to be here. If during the talk at some point you have any questions, please feel free to just interrupt me because I cannot see all of you. So if you raise your hand or so, I may not be able to see it, but feel free to just stop me and ask a question if you would like to. So this talk is about network structures and epidemics, and it's joint work. So some of the work is the work I did during my PhD, so some time ago, together with Remco van der Hofstad and Johan van Leeuwarden. And some of the work I will be presenting later is more recent work, which I did together with Ivan Crijven, who is at Utrecht University. So in general, this work is about epidemics and network structures and how they can actually, so how one influences the other. So, just to show a network, I can start by just showing what a network is. I guess most of you know, but this is a very particular network. This is my own LinkedIn network. So you can see myself right here and all my LinkedIn friends. And the connection means that two of my LinkedIn friends also know each other. So this is just basically a social network. And as you can see, these networks may look very complex, but actually very often if you try to look for them, you can find very beautiful hidden structures in these networks, such as this one. So this is the exact same network, but now it's just been so the layout has now been done by some computer algorithm, and then you can see that it places me in the center and all my LinkedIn connections are around me. And you can see that, for example, so there are all kinds, my LinkedIn connections organize themselves into some sort of groups. And of course, if you start looking at these groups, so for me, it's not very difficult to find where these groups are coming from. So yeah, of course, people I once met in China know each other very well because we were there together, but they do not know my family or friends from sports or people I met at Twente University. And I guess if you look at your own social network, you will find very similar of these groups, which we call community structures. And these community structures are actually present in many networks. So of course, in social media, they are present very often because people just have groups of friends that all know each other quite well. But also here's another example that I like very much. This is an example of a communication network of a specific country. So nodes here are people. And a link means that these people once communicated over the phone. So this is a mobile phone communication network of a given country. So is there anyone who dares to guess which country this communication network belongs to?
I have a question then. I mean, each node is a single person, or is that a whole?
Yeah, so I think so. It's indeed, so it is aggregated, and of course this is also not entire country. So it's not like this is a country of only so many inhabitants. But I think so, and part of it is aggregated, and it's also only a sample. But I think it's probably representative for the country.
Is it Korea?
Korea, yes. So Korea would be a very good option indeed. Then you would have North Korea and South Korea. So that I think the Korean network will look very similar, but this is actually Belgium. So we have the French people right over here. And we like to talk to each other a lot. As you can see, the Flemish people also communicate a lot. But as you can see, these are really two different communities, as we call them in network science. And there's, well, of course, there's some interaction, but you can really see that this is two different communities. So community structures in networks are present, well, in many cases. But then the question is, so how do these structures that are present in networks, how do they actually affect how an epidemic spreads? And so epidemics on networks have been investigated for a very long time. And one of the most simple models for a network, which allow you to mathematically easily investigate how an epidemic spreads, that is the configuration model. So the configuration model is a model that generates random networks. And you can generate networks with any kind of degree input. So for example, in the configuration model, I can say I want to have a network with, well, 3 nodes that have degree 2, so that have 2 connections, and 2 nodes that have only 1 connection. And then what this configuration model does, it just selects one of these. So you say, okay, so this one, I will start with this one, for example. It's just random, and you pair it completely randomly. So for example, to this one, then you start choosing a random neighbor for this one, for example, like this. And you finish, and then you get a network with exactly the degree sequence you want. So as you can see, it's possible that you end up with self loops or multiple edges, but if you make the network very large, then this will happen only with a very small probability. And what the nice thing about this network model is that you can actually, for example, if you have a network data set, a very large network data set, then it's very easy to extract the degrees. And then you use them as an input for this model. And this model then generates, you can generate random networks. So it can generate maybe 1,000 networks that should be sort of similar to this network. So then you could do statistical tests. So for example, you could test all these 1,000 networks and see like what makes them different from the original data set. So this is a model that can generate sort of benchmarks for networks. And one property, so why people analyze this model very much, is because it's very easy to analyze. And that is because this configuration model has the property, so we call it is locally tree-like, which basically means the configuration model, so this random graph model, will end up being a tree, or almost a tree. So that means that if you start at some node here, of course, this node has some neighbors with some distribution D. Have different numbers of neighbors, they will be different. So they will not be connected like this. So there are no cycles, for example, this, or no connections going back like that. So this model is actually just a tree with specifics, or a tree, or as we call a branching process, with a very specific offspring distribution. So with very specific ways of having how many children there are. And that, of course, depends on what degrees you choose as input for the model. And because of this, this model is extremely easy to analyze. And because of that, also many properties for epidemics have been derived. So for example, one type of epidemic that people study quite often is a very simple epidemic where one person starts to be infected at random. And then every infected person just flips a coin for all of their neighbors. And with probability P, they infect their neighbors, and with probability 1 minus P, a neighbor is not infected. So for example, this one may infect these 3 neighbors, but maybe not this one. This one was lucky. And then these 3 newly infected ones, they do the same thing. And at some point, this epidemic stops because, for example, this one doesn't infect this one, and then we see the epidemic stops. And this is actually, this is a very simple epidemic model, but you can show that this is actually equivalent to this SIR model that you often hear about, but only like if you're interested in the final size of this SIR epidemic. So then in this case, you would be interested in at the end. So suppose this process stops, then what is the fraction of network members that are infected? So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 9 infected ones, and in total we have 13 nodes. So the final size of the epidemic would be 9/13 as a fraction. And you can show that this is actually equivalent to if you would have this more complex SIR model that you hear about very often, and that then you're interested in, like, once we're done with this epidemic, how many people have ever had this infection? So then you should choose this probability P in such a way that it actually corresponds with the right type of SIR epidemic. So this is what we're often interested in. So you have an infection probability P, and you want to know how many nodes are infected at the end of the epidemic.
So I can.
And what you. Yes.
So if you come back to the previous picture, why isn't this fraction impacted by the structure of that graph?
It is very much, yes. So indeed, so this is, it's of course affected by randomness, because this process was random. And if this person would have infected this one, then it would be larger. And it is very much impacted by the structure of the graph. So that is also why it's very, so indeed, that is also what the point is of this talk, is that you have to be very specific on what you think, what your mathematical model for a graph looks like, because yeah, for example, if your graph has only isolated nodes, then I can tell you that that in the end you will have only one person infected. And if you have a complete graph, then you will have a lot of infections. So it's very much influenced by the structure of the graph. And that is also what a lot of people are interested in, is how can we actually predict what this final size will be given a specific input graph.
Yeah, so but when you start with your SIR model, you do it on the graph then, you mean?
Yes, yeah. So this would be an SIR model on the graph.
Okay, sorry.
Yeah, so every node indeed then is either S or R. They, depending on how many infected neighbors you are, you also get infected with a specific rate.
Yeah, sorry.
And that is indeed a bit.
I didn't understand that. Okay. Sorry for the question. Yeah.
No problem. I think it's a very good question. So indeed, so these SIR models, so you can define them on a population level, and then you basically assume that your graph is a complete graph, that all possible connections are there, but it's also very much influenced by which connections are actually present in your graph.
Thanks.
So as I said, for several, so you can try this, like how this plays out in many graph structures. And typically what you see, if you increase this infection probability P, and here we plot this fraction of infected people, and we have a very large graph, so we assume thousands of nodes in the graph, then you see that often when the infection probability is very low, then the outbreak will be so small that, well, you could say that the fraction of infected people will be on 0, or of course, it will not be precisely 0, but it will be very close to 0 if your graph is large enough. And then there is one point, which we call the critical probability, where there's a change. At this critical probability, you will see that the final size of the epidemic, all of a sudden, it becomes larger. And then, of course, if you're infected, so the probability that you infect and that someone else increases, then you see that the fraction of people that get infected also increases, which of course makes sense.
Sorry, just one question.
And for this, yeah.
I mean, this is not graph independent, right? I mean, these numbers you have here.
No, it's definitely not graph independent. So, but of course, I think if you try any graph, then often you see something like this, but where this point PC is, that changes also what is shaped. The shape is not always like this. It can have very weird shapes.
Okay.
Sometimes this PC is even 0. So yeah, this also depends very much on the graph. But typically you do see, if you look at data, you do see something like this, which looks sort of convex, has some value of this PC. But what this value is very much depends on the graph.
Yeah, thanks.
I guess it also depends
So
on.
in on this,
Sorry, Clara. I guess it also depends on where you start the epidemic. Is that right? Or do you sort of choose randomly this graph from a certain class?
so yeah, so it of course it depends. So you usually start at random, and then, for example, if your graph has two components, then it's possible that sometimes you start in the epidemic in the one component, sometimes in the other. So if you want like mathematical results, then of course you really have to assume that you draw your graph from a specific model, because indeed otherwise you can have very weird looking shapes where it matters very much where you start. But often you see that most networks also that you see in data have one very large component and maybe a few extremely small ones. So then the probability that you start there is also small. So then if you average over several simulations, then the probability that you see an epidemic starting in this very tiny component is also small. But in general, I think, yes, this is definitely, so this is definitely a random variable. But for this configuration model, you can actually show that if you have this model where you start with the degrees as an input, then you can actually show what this PC is. So it's 1 divided by the expected number of neighbors minus 1. And you can show that if your infectiousness is smaller than that, then you will have asymptotically. So if you have a very large graph, you will have a fraction of 0 infections. And if it's larger, then you will have a positive one. And you can actually also write out an explicit equation for what you expect this to be. But that one is not very beautiful, so I won't write it down here. It depends also, of course, on what the degrees of these graphs look like. But I thought I can give some intuition why this thing occurs. So what we saw in this configuration model, it looked like a tree. And because of that, so if you start, well, of course, first one vertex start infected. And on average, he has expected value of D neighbors. So D is the degree of a randomly chosen vertex. And on average, you infect P out of them. So in generation 0, we have 1 infected vertex. And then in generation 1, so that is those people, those will be on average the expected degree times P, because he infects a fraction of P vertices of his neighbors. Then here, so in the second layer, it becomes a bit more complex, because as you can see, so this vertex will have a specific degree. For example, in this case, it has degree 2, but 1 is actually already used up to connect to its infector. So this vertex cannot infect, it can at most infect 1 person and not 2, even though its degree is 2. So that's why the -1 is here, because 1 degree has already been used up to connect to your infector. And also here there is a D star, which is not the same as a random degree, because your neighbors are not the same as you. So if you think about it, if you choose a random friend of yours, it's likely that this person has more friends than you have, because people with more friends are more often counted as a friend. The probability that you are friends with someone with 1,000 friends, it's much higher than the probability that you are friends with someone who only has 1 friend. And because of this D star is slightly different than D. So this D star is this is in this case, the average number of friends of a neighbor of yours. And this will be a bit higher than this D. And you can also compute it. But on average, so this person has this D star and a -1, because 1 person is already used up neighbors, and P will be infected out of them. So in the second generation, we first had the first generation, and each in the first generation infects on average this number of vertices. So you will have this many in this second generation. And then you can iterate this, and you will see that in generation K, you will have this term times P times this thing to the power K -1. And from here, you can see that if this term here, if that is smaller than 1, then this will die out very quickly. So then in generation 100, you will probably see 0 infections. But if this is larger than 1, then of course this grows and you have this large outbreak. So you can actually view this thing as some sort of R0 parameter, because this actually tells you how many people does one infected individual on average infect. And then if this is larger than 1, you have exponential growth. And if it's smaller than 1, it dies out in a large limit, network limit. So this is why this, if you say, okay, this equals 0, then you get that PC, so the critical probability is 1 divided by this D star minus 1. Yeah, so that's also on this slide. So that's actually how you can easily compute these things in this configuration model. And why does this heuristic proof work? Well, it works because we have this very nice tree structure. Because we say, okay, this person maybe infects on average this amount of people, and we know that they are not the same people infects, or that this person has already infected. But if you have loops like this, then for example, in this case, we say this person infects on average 2 persons, for example, and this one as well. But in fact, they are the same person, so we shouldn't count it twice. So in these situations, this calculation wouldn't work. And that's a bit unfortunate because we just saw that in most networks, actually you have a lot of these groups of friends where everyone knows each other, lots of short cycles. So this configuration model is very nice because you can get very easily, you can get mathematical results, but it's not the most realistic network model. So because of that, we defined a bit more difficult model, which doesn't start with vertices, but you actually already start with small groups. So here we have a group of friends, here as well. And then we only randomize the connections between different groups. So for example, you can end up with this graph in the end if you randomize these connections. But of course, it's random. So if you run it again, you may end up with this graph where the connections are now slightly different. And then by using this model, you can actually investigate what is the effect of communities, because we were able to derive expressions for how big will an epidemic become on such a model. So these things, they are actually things that you can define in your input. So you can have any shape you like. For example, you can say half of my groups of friends will look like this, the other half will look like this, or you can choose some different shape you like. So, but then by comparing to this original model, where you actually randomize all communities. So note that if you define these models, if you compare them in the right way, you can see that here we have the same amount of connections as here, the same amount of vertices. And you can also see that every vertex has the same degree in both models. So the only difference is that here we constrain some of them to be inside groups, and here we do not. So then if you analyze how an epidemic spreads here and how an epidemic spreads here, you can investigate what is actually the impact of these groups of friends. And what we saw is that the impact of small groups of friends is actually not trivial, because it really depends on what your groups of friends look like. So for example, if we only had these triangle groups of friends, so very small groups of friends, then here we have again, so this infectiousness against the people are infected in the end. And you can see there, so in this, without any communities, if you do not have any communities. So having these groups of friends actually speeds up an epidemic. But then later on, you see the other way around, that having these groups of friends actually slows down an epidemic. And then if you make these groups of friends a bit larger, then you see that apparently now, if you have these groups of friends, there are always fewer infected people than if you have these groups of friends. So whether groups of friends speed up or slow down an epidemic, that is actually really dependent on the exact shape of these groups. And you can think about it. So if you think about these epidemics like domino stones, then you can sort of intuitively guess why it's not so clear what happens. Because on the one hand, of course, if you have a group of friends, so in this case, this would be such a spiral, then of course, if the first person of a group of friends becomes infected, then the entire group will also get infected. Because there are so many connections within groups, so if the first one falls, then the entire group will also get ill because they know each other so well, it's very likely that they will infect each other. But on the other hand, because these groups are so well connected, less connected to the outside, it's possible that, for example, if this domino stone doesn't happen to fall, so that would be the connection from one group to the other, then also actually this entire group and all these groups of friends are all saved. So on the one hand, so these groups can actually speed up an epidemic because entire groups get infected at once. But they can also slow down an epidemic because epidemics get contained within these small groups and do not go out. And which of these two happens, that depends very much on the exact shapes of your groups, which is of course a bit unfortunate because then you would have to really calculate it for the network you're interested in. So we also investigated this for some real network data. So then we tried, so if you have a data set, of course, you can find out what are the degrees of all the vertices. And then you can make a model like this of the data set. You can use some detection algorithm to extract where the groups of friends are in a specific network. And then you can randomize the connections between the groups of friends to create this model. And we also added an intermediate layer where you also randomize connections within groups of friends, but you do constrain them to be within the group. So they cannot, this connection cannot go like this, but it could go, for example, to this one. And then if you look at, so here I show some results on two network data sets. So on the first one, so the black line is what an epidemic behaves like on a data set. And these two are these models that both include the community structure. And as you can see, by using this community structure as input, you are really able to very well predict what this epidemic behaves like. But if you do not take these communities into account, then you actually overestimate the number of infected people. So in this case, actually the community structure in this network makes an epidemic slow down, you could say, or it makes it smaller, because these communities make sure that fewer people are infected. But then if you look at another network where we did the same thing, you can see that the opposite happens. So again, so these two models are a reasonably good prediction of what happens on the network data. So if you include these community structures, you can reasonably well predict how this spreads. But if you do not use them, you see that in this case, you're actually below the actual value. So here, in this case, and these communities actually, for some reason, help an epidemic to spread. So which of these effects appears really depends on what your network looks like. And so just for simulation, we also ran this SIR model. So now we see over time how many people are infected. And then for these both data sets, you get a very similar thing. So the data is now the blue line. And as you can see, it's reasonably approximated by the models with communities, but the pink line without communities, again, overestimates the number of infected people. And here again, the pink line underestimates the number of infected people. So also here we see that community structures in network can affect the epidemic spread in different ways.
Can I ask a question?
So the conclusion of this part is that communities can either inhibit or enforce epidemics. And which of these two appear, that actually depends very much on the exact network structure. So from here, I would like to go to then, for the last couple of minutes, I would like to go to some more recent work, because often you're not only interested in just predicting, well, what will be the final size of the epidemic, because once you know that an epidemic is there, of course, you take some action. You don't just want to know, okay, now we know that 80% will be infected, let's stop. And one of the ways to reduce that is contact tracing. And in this work, we also wanted to investigate what is actually the impact of the network structure on how effective contact tracing is. So we investigated some contact process. So here, in these pictures, so we assume that this is actually the infection tree. So this person infects all these ones, and this one then infects those ones, this one infects those ones. So these are the infections that take place. And then we assume that with some probability, we call it 1 minus PS, vertices get tested and say, okay, I have some, maybe I have a cold, let's get myself tested. Because some people may be asymptomatic, they may not or may not want to test. So some people get tested, other people will not. So these red people are the people who say, okay, I will get tested. And then, of course, if you're tested positive, then they try to find out who is the person that infected you. But this is not always possible to find out. So we assume that with some probability, all these people who got themselves tested and tested positive, that some of them with some probability PT are actually able to identify, well, this is the person who infected me. And then this person who infected, then they also, maybe they didn't get tested themselves because they didn't have any complaints, but now they know that they are that they should also get in quarantine. So that means that because these ones will go into quarantine, some of these infections that this person would have made will not appear. So this person quarantines, of course, only after he has been reported. So some of these infections may already have happened maybe before he infected this one, or it may have happened in between the time that this person was getting tested and that this person says, okay, you infected me. But then once this person knows that he is also positive, so then he will quarantine. So that means that with some probability, some of the other contacts the other infections will not happen in the end because this person is in quarantine. Some others may still happen because they already happened before, for example, this reporting took place. And we model this as a specific probability that for all these later infections that they will still be there or that they will be removed. So I hope this process is sort of clear.
Yes, so you just change the network structure for a period of time or something when these guys go into quarantine?
Yes, so indeed, this, so once we go into quarantine, then it is removed. And maybe if it would be a larger one, then some others would also be removed.
But you do that for some period.
And also once it self-reports, then its next infections will get removed.
Right, but you do it for a period of time or something. Then you link them back into or how does it?
So now we do it so now what we do now is we do it statically, so that this person so that these links will be removed forever. But of course, in theory, you would want them to probably reappear. But in this case, these are also infection links. So these are not like social network links. So these are infection links. So of course, this infection can of course still appear later, because if this person then gets infected again, and then for example, this infection is prevented, but if this person would get reinfected, then in theory he could again infect this person. But for now, we assume no reinfections.
Okay.
So that second infections cannot happen.
Thanks.
So as I said, so what we were interested in is how does the effectiveness of a tracing process depend on the number of network, or well, on the shape of the network. And some intuitive results on this had actually already been published. So one result that was, I think, published quite early in the beginning of the pandemic is that there was also, they said, okay, well, if you have a tracing process, then there are actually two things that play a role if you want to investigate the network structure. So one thing is that you're more likely to be infected by a high degree vertex. Because if someone infects maybe 100 people, you're more likely to be one of them than if someone only affects one person. So if you are infected, it's more likely that your infector has a high degree than it has a low degree, because high degree vertices infect many more, so you're more likely to be one of them. And then they said, well, there's another thing as well. If you assume this tracing process, if you infect 20 others, then it's also more likely that one of your 20 infectors is actually reports, tests, and also actually manages to point to you as an infector, because there are just many more people who you infected. So the probability that one of them succeeds in blaming you is also higher. So they say, well, this is actually some sort of double friendship paradox, because high degree vertices are more likely to infect people, and then also, again, more likely to be traced by someone who is infected. So they said because of that, this tracing process should be extremely effective if you have heterogeneity in your network. So what does that mean? So that means that if you have some vertices which are, well, so-called super spreaders that infect many people, and if you have others that only infect a few. And they said, well, on these types of networks, it should be extremely effective because this tracing process is actually able to take out these super spreaders very effectively because of these two observations. But then, of course, there's also another thing that comes into play, because indeed, if once you assume that this process takes no time at all, then indeed, once someone is identified, then all infections of this person drop. But in reality, of course, this is not the case. We all know that getting tested and getting the results back, tracing and so on, takes time. And in this time, and also, of course, it takes time if you get infected, it also takes time before you get symptoms and before you get tested. And in this time, your high degree infector may actually also infect many others. So it's possible that, yes, you are able to point at this person and say, okay, this is my infector, and he is actually a super spreader. But that in that time, this person has already infected so many others that it's in fact not even so beneficial anymore to identify this person. So we took this into account by assuming that not all connections of an identified vertex are removed, but only some of them, because some are maybe have happened in between this delay. And then we investigated what is the effectiveness of this tracing. So here we have two networks. So one is a heterogeneous network. So these are networks with some super spreaders and, well, some people with intermediate degree, some people with low degree, and a homogeneous network where every person has the same amount of connections. And on average, these two networks have the same amount of connections, but they're just like, well, they're more unfairly distributed in the heterogeneous network. And again, so here you see this infectiousness parameter, and is the final size of an epidemic. And the dotted line is if you would not do any contact tracing. And this one is if you would do contact tracing. So here you can see that tracing actually does reduce the size of an epidemic, because here it was right here, and it goes down all the way here. And the same is for a homogeneous network. And here you see that in some cases here, even if you would have an epidemic that is actually large, in some cases, this tracing process is actually be able to push this R0 below 1 so that you actually do not have a large epidemic. So then what you can do is you can say, okay, by how many infections does this tracing process, how much does that remove? So by just subtracting, so we know how many would be infected without contact tracing and with, so you can just subtract them and then say how many infections does it actually prevent? And we plotted that right here. So here you can already then see that it's actually not quite clear that on these heterogeneous network, it's not true that that contact tracing is always more effective on these heterogeneous networks. You see, well, here it's more effective. Well, that is also because on these homogeneous networks, there's no giant outbreak. But even after that, you see that for some infectiousness parameters, then, well, actually, this tracing process works extremely well on homogeneous networks, but less so on the heterogeneous one. And then after some point, it flips. And why this exactly happens, I don't know. So we got the equations and the simulations. But so I don't really fully understand why this shift happens, but it's clear that the network structure plays a very important role. And what we finally did is we also investigated the effect of what if you add these communities again. So this is the very simplest case of adding triangle communities to your network. So we saw before that adding these community structures can have a very important impact on how fast an epidemic spreads. So now we want to know what is the impact on this tracing process. And now here again, you see how effective a tracing process is. So again, if you have a heterogeneous networks, then you see that, well, if you have these structures, then tracing is less effective than if you do have them. But in this homogeneous network where everyone has approximately the same number of friends, then you see then here it's not even clear. Sometimes actually, it's the other way around for most of the parameters. If you have communities, tracing is more effective, but for some others, it's not. So I think also here the conclusion is that if you want to investigate how much contact tracing helps you, you really need to take this as explicit or like all knowledge you have on a network structure into account, because well, you can see that there can be quite a difference between what you assume on the network structure. So yes, so both heterogeneity and community structures affect these the effectiveness of contact tracing in a non-trivial way. So that was my presentation. So if you have any questions, feel free to ask.
Yes, thank you very much, Clara. I think Wout had a question.
Thanks very much. Yeah, thanks for the nice talk, first of all. I was wondering, in the example you showed where you had this email network and the internet network, and you said in one, the community is sort of lower, and the other, the community structure increases the threshold. So was there any noticeable difference in the type of communities that appear in email network versus the internet network?
Yes, indeed. So for this one, so we did look at them, and what we did notice is that in this email network, the communities in this case were more like close, like many connections within, and maybe a few going out. And in this internet network, it was maybe, so a community consisted of well, a bit fewer, so it was less dense, you could say. So for example, and then more are pointing out. Okay. So because then actually it helps, because adding triangles gives you some robust. So because then if you have a triangle, then for example, if this epidemic, this one doesn't infect you, then you can still be infected like this. So adding triangles actually can speed up an epidemic, but then of course you do not want to add so many triangles that you waste a lot of edges only infecting people who were actually already going to be infected and then never infect more people. So I think it's some sort of a trade-off there. But we also tried, for example, if you well have the fraction of edges inside the community and outside the community. If you can predict something better using that, but actually that didn't work. So probably something more is also present. But here it seemed to be that it is something with like the fraction of edges going out versus all them going in.
Thanks.
Can I ask a question? So I was wondering if you look into connection with the eigenvalues and eigen vectors of your agency matrix of your graph. So, so if you look at a Markov process on a graph, then the memory of your Markov process, so how far it can spread, let's say how far you can predict in the future, depend on your eigenvalues, on the eigenvalues of your agency matrix. So maybe you can, I mean, maybe that could be interesting. And
yeah, I think so, definitely. I think there's a very strong connection indeed between eigenvalues and both community detection and spreading processes. But to be honest, I'm not so much of an expert there, but I think it could definitely be very interesting.
yes, so you can look into maybe Markov processes on graph, and maybe that could help you. But the difficulty is that in your case, you have the branching thing, and so I don't know how to do it with the branching in that case. But definitively, in case of just a simple Markov process, and your memory and your predictive information. So if you look in the past and if you look in the future, how far you can predict in the future. So how many nodes far apart from you for which you can predict. I don't know, maybe this is not very clear, but how far you can predict in the future depend on the structure of your graph, on the topology. And so it depends on the eigenvalues and of this agency matrix, on the first eigenvalues.
Yeah, and I think people are also studying. So I think a lot of people are then, for example, for random graphs, studying the expected adjacency matrix. Mm-hmm. And maybe this would also work then in this situation, that you sort of take the eigenvalues of the expected adjacency matrix and then use it like that indeed to account for this branching process.
Yeah, so in case of without the branching process, what you would do is that you will look at the average. I mean, the predictive information is already average over all the graph. So let me see. I can't remember exactly how it works, but it will be already average over all your graph. So that will be already an average quantity.
Ah, yeah. Thanks for the comment.
Yeah. And then the second thing is, so maybe this is difficult to compute, but an interesting quantity to look at might be this correlation between pairs or nodes, correlation function between pairs of nodes. So I don't know, like even if you don't have the graph structure, then how big would a branching process spread would be given by some type of correlation, spatial temporal correlation function. And you will look at the characteristic length of this correlation function. The same, I don't know on graph how hard it is to compute this type of function. But yeah, so I think, yeah, so basically eigenvalues of matrix, of agency matrix and correlation functions are the two keywords I would tell you here.
Yes, thanks. I'll write them down.
Can I ask a question as well? First of all, thanks for the talk. So I was wondering, you showed that the structure of the graph really influences the effect of this tracing thing. So is it possible that you have some kind of very weird graph where tracing actually helps the infection? Or could you prove that tracing is always a good idea?
No, I think in our model, it cannot help because it only removes infections. So that's the only thing that tracing does. So if you are, so in this case, I think it cannot, because so it says, well, if some person is traced, then some of the infections will be removed. So you always have fewer infections, but I think it's of course possible that if you have a very large graph, that you can create some weird graph where asymptotically you don't see this effect anymore or so. I wouldn't be surprised if this is possible. But I also wouldn't know how to construct such a graph, so.
Okay. Yeah. To me, it was not immediately clear that that it would always be a good
Yes,
idea.
and I think also that is because we really assume that this infection, so if it's removed, it will never take place. But of course, the comment I had in the talk as well, of course, it's also possible that this person gets later reinfected and then infects this person again, and maybe because of that a larger epidemic start. So I guess if you take the temporal effects into account as well, that people can get reinfected and then an infection that was first prevented then happens again, and then because of that the second wave starts, then it can actually be, I think, so we started looking into that for a bit by looking into different waves or so, but that didn't give us very interpretable results, so we stopped it after a while. But I think that in that case the results were also less clear on the tracing process, so I think it may be possible that in that case indeed tracing can do weird things and cause second waves.
Okay. Yeah. Interesting.
Yeah, of course, depending on how your graph, what your graph looked like.
Yeah. Okay. Thanks again.
So I also had a question. At the moment, this is all on a static network, except for the contact tracing, which introduces some sort of cutting of edges. But I was at a talk recently by a sociologist who was also looking at doing Asian-based modeling on epidemic spreading. And they had a model, a simple model for how the network actually changes because of the information that the pandemic is around. So you might sever links, or you could also then, people were talking about this making a bubble. So I was wondering if there's some sort of, any hope, first of all, of studying that, and then also some interplay between the spread of the pandemic and the amount of clustering into communities, so that more communities form when the epidemic is spreading.
Yeah, so I think indeed, so I mean, so the beginning of this work on epidemics and communities was done some time ago. And I think right now there's also in general a lot of research on, they call temporal graphs, where connections change over time, nodes change over time. And I think that could be used to analyze also epidemic spreading on models where it does change. And there you also see typically that it also, for example, depends on how fast does your epidemic spread and how fast do your connections change. Because if your epidemic spreads extremely fast, then, well, everyone is infected before you start adapting your behavior. But if for example, if your connections swap so fast and the epidemic spreads really slowly, then it becomes also very weird. And then there's in this intermediate regime where they change time on sort of the same scales. That is typically also what you see in those types of models, but I have not tried to apply it to these clustering phenomena. But I think that would also be a very interesting approach.
Any other questions?
Yeah, I just want to ask something. So how much do you have any analytic control over these results, or is just all of it simulation, or do you...
So no, actually, this is this was published in a more physics paper. So then you also need simulations, but these lines, they are all analytic, and then the versus they are the simulations. And so for the real data, I think we did simulations, I think, but in general, we also have the equation for the exact results. So for example, if you first extract these community structures, then we can analytically find this entire shape of the epidemic curve.
Okay.
So, and in theory, we could have also done that for the data. I think, this is, I think, also an analytic function. Only for this SIR, we do not have any analytic.
For the time dependence, there are no analytic results.
No, so I don't have to, especially not for this model. I think for time dependent epidemics, there are some results on some models, but I'm not sure. But here we do not have any time dependent results.
Okay, thanks.
So if there are no further questions, maybe we can thank Clara again.
Yes, and thanks again for inviting me, Janusz.
Yes. And I can suggest reading some of those articles of Clara's if you're interested in getting more details on this.